Hello wonderful person, this is Anton, and in this video we're going to return back to TRAPPIST-1 and talk a little bit more about the recent studies and recent updates about this incredible system. Let's find out what the scientists have been studying, and welcome to What the Math. So in the last few months, specifically in the last, I guess 5 or 6 months since I made the last video, there have actually been quite a lot of studies. As a matter of fact, here are just some of the recent ones from the last few months. But the bigger studies were basically related to the actual nature of the exoplanets and essentially what's on the inside, what do they contain, and how do they possibly look, and most importantly, do they have any water or livable conditions on the surface. Now, by now, you should probably be aware that TRAPPIST-1 basically has 7 confirmed terrestrial planets, or Earth-like in a sense, in terms of at least mass, but it's not necessarily true of their actual composition. And so the recent discoveries made the actual error of predicting the mass and the density of these planets much smaller than it used to be. We went down from about 10% certainty to basically about 90% certainty of what is probably happening in this particular system. And right here, you're actually looking at TRAPPIST-1e, which is right now the most sort of hope-giving and the most inspiring planet that we've discovered, exoplanet that is, because it does seem to be very Earth-like. Anyway, let's take a look at some of the recent discoveries, and this is mostly based on a paper from Simon Grimm, who is kind of the principal investigator for these studies. And also this paper right here, Interior Characterization and Multiplanetary Systems, TRAPPIST-1. This is by Caroline Dorn and also Simon Grimm as well. So what did they actually discover, and what do we know about TRAPPIST-1 now after about 2 years of basically studying the system full time? Well, first of all, let me actually just explain to you how they even discovered all of this stuff. So originally, the way we discovered the planets is by seeing them sort of pass in front of the star, and so that way we were able to see the actual size of the star of the planets, because we kind of knew the size of the TRAPPIST based on analysis of other stars. We could then estimate or predict the size of planets because of the amount of luminosity that the star lost when the planet that you see right here passed in front of it. So this is kind of how we found the size, but we didn't really know the mass. And Simon Grimm's analysis involved the interaction of these planets between each other. Now, here's the cool thing about TRAPPIST-1. All of the planets here have what's known as a resonance. Basically, they're kind of connected in the way they orbit around each other. I think the easiest example of resonance can be actually seen right here around Jupiter. If you look at orbit of Io and compare it to orbit of Europa and then Ganymede, you'll realize that there's actually a direct relationship between them. For every 4 orbits of Io that you see right here, Europa gets 2 and Ganymede gets 1. So it's basically a 4-to-1 resonance. In TRAPPIST system, it's a little bit more complex than that, but there is a resonance, meaning that you can technically predict where a planet would be. Even without looking at it directly, you should be able to kind of predict where it is based on the resonance. And the resonance there is relatively complex, but it is there. And so what Simon Grimm's team did was basically compare the visual observation with the predicted resonance-based orbits. And what they discovered was that sometimes the planets weren't really where they were supposed to be because they were interacting with each other. And that way, using a very complex mathematics, they were able to actually calculate the mass for most of them relatively accurately. And so because these planets always sort of tug on each other, the gravity of every planet influences the other planets, the team was able to use what's known as an n-body simulation. Basically, this is an example of n-body simulation where all of these planets kind of influence each other gravitationally. They were able to predict, using multiple simulations, of what composition and, in some sense, what density and mass was the most appropriate for this system. And in the end, they actually achieved something like 5 to 12% error, which was a dramatic increase from a 90% error that we had before. And the results were actually quite interesting. So first of all, the density of all of these objects is anywhere between 60% of density of Earth to just a little bit over the density of Earth, so just like 1.01. So that means that our old parameters here are actually incorrect. The density that we used to have for a lot of these objects is kind of wrong. The analysis also showed that basically TRAPPIST-1c and TRAPPIST-1e, these two objects, are the most terrestrial of them all. They're basically the most rocky and the densest of them all. Here the density is actually wrong as well, so it should be closer to about 5. So we're going to change that. And then interestingly, we also found that at least 4 of these objects probably have quite a lot of volatiles. These are usually things like water. So in other words, there could be tremendously large amounts of water stored here, something like 200 times more than on Earth. So this planet, TRAPPIST-1f, this one right here, TRAPPIST-1g, also the closer ones, specifically TRAPPIST-1d and TRAPPIST-1b, may actually contain a tremendous amount of water. And for D, G, and F, what this implies is that they probably look exactly like this. They're basically these large frozen worlds, similar to Europa, similar to Ganymede. At least that's the assumption right now, with about 5% of mass as volatiles, basically as ices. They kind of may resemble Ganymede. On the other hand, because TRAPPIST-1b is really close to its star, it probably has something different going on here. And the assumption here is that it most likely has a tremendous runaway greenhouse effect, similar to Venus. In other words, if we were to take a look at this and compare it to the planet on our own, in our own solar system, it would maybe resemble Venus, except that much, much hotter. So, okay, this is maybe a little bit too hot. Let's make it a little bit less hot. It would have a very, very thick atmosphere filled with water vapor, and there will be a lot of volatiles here as well, but because it's so close to the parent star, it would just basically be all as very, very thick atmospheric layer above it. And because there's a lot of greenhouse effect here, it would obviously be just as hot as Venus, possibly even hotter. So this is kind of like a Venus representative of TRAPPIST-1. While on the other hand, planets D, F, and G that I previously mentioned may not have any complex atmosphere at all. As a matter of fact, the scientists studying these planets don't expect there to be any complex thick atmosphere. Or if it is thick, it's going to be very simple, simply containing things like nitrogen, not carbon dioxide, not CO2. This also implies that the closest sort of equivalent in terms of atmosphere would be an object like Pluto, that I'm going to briefly place right next to this object here, because we know that Pluto has a very, very thin nitrogen atmosphere. These objects may have something similar as well, but not a complex atmosphere like we have on Earth or even the ones on Venus. Although nevertheless, it doesn't change the fact that B, D, F, and G planets actually have a tremendous amount of water, or at least some kind of volatile similar to water. So in that sense, these are technically water worlds, even though they might not have liquid water. They might have just ice shelves like TRAPPIST-1d here, or a lot of water vapor like TRAPPIST-1b. So water worlds, but not really liquid water. And then we come to the biggest surprise, or I guess it wasn't really a surprise because we expected that, TRAPPIST-1e, which, as you can kind of see here, is actually sort of in a habitable zone. It does receive a little bit more heat than our planet Earth does at this distance, but here what we do expect is an object that might actually contain a lot of liquid water, because we do expect a lot of water here. But at the same time, it's also a little bit more dense than Earth, and may actually resemble something similar to a super Mercury than an actual Earth. So it's not an Earth-like planet as much as it is a very unusual liquid Mercury. The actual mass of this planet which I think is a little bit easier to see right here, is just a little bit less than the mass of Earth, 77%, and its radius is also smaller, but its density is a little bit higher. That actually implies that it's probable that this object received a very large collision early in its development that basically stripped the old TRAPPIST-1e off the actual mantle that kind of flew away and possibly collided with something else. And what was left was a very dense iron core, iron and magnesium specifically. And this is kind of what one of the explanation is, because otherwise it's very hard to explain why this object is so much more dense and has so much more iron and other metals inside than the other planets in the system. So this, in a sense, is a representative of Mercury-like planets, but at the same time it does seem to have what could potentially be atmosphere and also liquid water. So in some sense, this right here is actually the most Earth-like object we've discovered so far, at least according to the more recent analysis. Now, obviously, this doesn't change the fact that we could be still wrong about these objects, because there are other scenarios where all of this mathematics still works. Like, for example, maybe, just maybe, these planets are actually a lot less massive than we think, and maybe, just maybe, the actual density is wrong for all of them, and they all have like no water but very dense iron cores. But only the future studies will actually help us understand these planets a little bit more and help us understand if it's actually worth coming here and studying these planets in more detail. Now, I think I'm going to finish this video by going to this unusual, I guess it's an ice volcano or something, on the surface of TRAPPIST-1e in Space Engine. And we're going to take a look at what it all sort of looks like on the surface. But at the same time, we're going to wait for more papers to come out that might explain things that are going on in this particular star system a little bit better. As of now, though, this is one of the best mass and density analysis papers that I've read, and it's definitely something that will help the scientists in the future to study other star systems as well. Anyway, thank you so much for watching, and if you've enjoyed this video, maybe subscribe and share this video with someone who loves learning through video games and wants to know more about space sciences as well. Come back tomorrow to learn something else, and maybe even consider supporting this channel on Patreon, because it does help me a lot. And if you know any other cool papers about TRAPPIST-1 system or other unusual systems that you've discovered and want me to talk about, do post it in the comments below, or maybe even email me the actual paper so I can take a look at it. And here's with that volcano, basically the remnants of the old ancient volcano on the surface of TRAPPIST-1. It's all covered in ice now, but one day maybe it will actually explode again. And this is kind of what it looks like to stand on the surface or on the edge of this volcano in Space Engine on TRAPPIST-1e. Anyway, thank you for watching, space out, and as always, bye bye.